Welcome to the live session on partial differential equations. Please ask your questions in the chat box. Sandeep, are you there?
So, are there any students here in the live session? Please ask your questions in the chat box.
Vivek, you may please start. Sandeep is there.
Okay. Yes. Hello, Sandeepan. I'm Vivek, and today I'm here with Professor Sivaji Ganesh, who is the instructor for this course. You had asked some questions on the response form, so we're going to answer some of them. I'm going to answer some of them from my own part. I was a PhD student under Professor Sivaji Ganesh at IIT Bombay earlier. So you had asked as a first question that can most of the real life models be formulated into PDEs? So as an answer to this, I would like to say that yes, there are a lot of models in the physical sciences that can be formulated into PDEs. And that has been the movement since the 16th century to until now. But more recently now there has been a shift towards other kinds of models, not just partial differential equations, but differential equations which involve other kinds of terms. So there would be algebraic equations coupled with them, or there could be what are called as fractional equations coupled with them, or there could be also integral differential equations. So there has been a move away from partial differential equations, and it is now felt that partial differential equations may not be sufficient to solve all real life models or to formulate all real life models. But they have been very successful and very useful in formulating models from real life. As a second question, you're asking how difficult are the solutions? As you are guessing, real life models will have various parameters that need to be taken into account. So as far as real life models are concerned, real life models definitely have a lot of parameters. But for example, for someone who is interested in studying mathematics or pursuing mathematics as a course of study or for their research, they would not be concerned with so many parameters. A primary aim for a mathematician would be to start with models which have a fewer number of parameters. So we would be more interested in proving the existence of solutions or describing solutions for model systems that are simplified as much as possible, and not necessarily our models will have everything that is taken into account at the same time. So one of the aims of the mathematician is to formulate the model in as simple a way as possible so that it has the fewest parameters possible. And I definitely think that it would take a long time for us to reach the point where we would be able to consider a lot of parameters in the same model as far as mathematics is concerned. Because in mathematics, at the beginning, you only study single equations, and only later on you study systems. And if you have more parameters, you're probably more likely to have a lot of a system, a large system of equations rather than a single equation. And systems are definitely more difficult to study. Okay, so if you have any questions related to that, please write in the chat box. Otherwise, I will proceed to the other questions that you have asked us.
Say my comment on the question one would be, can most of the real life models be formulated into PDEs? First of all, you have to decide what is that you want to study, and then you have to convert that into a model, mathematical model. So to do this, you need to understand what is important, what is that you want to study, what you can afford to not model, and then you model. And then you have to validate the model. You have to check whether the model is indeed a good model. And if you want to model the most general thing, the equation is going to be more complex. As Vivek said, it won't be generally PDEs. It will be a mix of several things, PDEs, integral differential equations, and so on. So many things are involved. And then question comes, can you study? You have a complicated model, can you understand its solutions, which is difficult. So you have to take equation by equation, and every equation will have its own complexity. So you must pay attention to that specific thing. It's not that you have a general theorem that any model can be solved or anything like that. Yeah, go ahead with the second question.
Yes, sir. As a second question, Sandeepan has asked us, how deep does the independent study of PDEs go as per research requirements? Okay, in the meantime, Sandeepan has also raised another question in the chat box before we move on to the second question. Sandeepan has asked us, what about problems in nonlinear dynamics? And indeed, it is true that nonlinear problems are definitely more difficult compared to linear problems. There are more tools available for linear problems. You can use Fourier transform, you can use Fourier analysis, you can use other kinds of tools that are available to you in linear dynamics, which are not available to you when you move on to nonlinear dynamics. So certainly studying nonlinear problems is much harder. In that case, moving on to the second question that was raised by Sandeepan. He asks, how deep does the independent study of PDs go as per research requirements? So I will put forward my opinion, which is that PDs is one area of mathematics which is truly interdisciplinary in the sense that you have interaction between analysis, algebra, geometry, topology. You have interaction of various branches of mathematics coming together in PDEs, and many branches of mathematics have also developed as a result of first studying PDEs. So definitely one can go very far if one wants to study PDEs. One can study PDEs which have a geometric bent towards them. One can study PDEs on graphs, which would require some knowledge of topology perhaps and geometry as well. One can study one can combine different areas in your study of PDEs, but which does not mean that a simple PD on its own does not have enough depth. A simple PD on its own would also have a lot of depth, which one could pursue for sure. But yes, if one wants to go far in research um, and find out new problems and find out more difficult problems to study, then they have to study interactions between different branches of mathematics.
Yeah. Any other question?
Yes, Sandeepan, if you have any more questions regarding this second question, please raise it in the chat box. Meanwhile, I will move on to the third question that you have raised, which says that, could you please tell me some fields in analysis where PDEs are used extensively? So regarding this, I would say that it has mostly been the other way around in the sense that analysis has been contributing to partial differential equations for a long time, and of course the motivation for studying motivation for studying analysis, such as harmonic analysis and functional analysis, has come from partial differential equations, and partial differential equations have extensively used these areas of analysis for their study. Functional analysis and harmonic analysis are integral parts of studying partial differential equations, and perhaps time has come for partial differential equations to reciprocate and answer questions in analysis if it is possible. But the only example that comes to my mind is the famous example of Ricci flow, which is perhaps a contribution of partial differential equations towards geometry, problems in geometry. Other than that, perhaps there are applications which are very extensive of partial differential equations in things such as image processing, and I guess now there will be a lot of applications to machine learning as well. So as a question, Sandeepan has asked in the chat box, I have actually studied a bit of topological dynamical systems in my master's. I would like to know how are PDEs used in such systems?
Yeah, PDEs are also dynamical systems when there is a time involved. ODEs also. The only difference is that in ODEs, the trajectory, that is the solution, as t varies, as the time varies, the solution will be traced in Rn, whereas in equations like wave equation or heat equation, where there's a time dependence, it's actually in function spaces. That is, it takes values in infinite dimensional function spaces. I think that's a major difference. And therefore, once you are in infinite dimensional spaces, there is always lack of compactness. So there are other notions of compactness and so on. So one can study dynamical systems with different topologies. I think Vivek can comment on this.
Yes, so certainly people do study PDEs with the topological dynamical system framework in their mind. From what I can recall, there is some work that people do in the case of Navier-Stokes equation, for example, where they study things like self-similarity of solutions, which is studied from a topological dynamical system point of view. And as Professor Shivaji mentioned that uh, uh, compactness is lost when we go to infinite dimensional spaces. And so we cannot study the standard topologies on these spaces, and we have to move on to other topologies where compactness can be regained. So, for example, in the context of partial differential equations, we are very much interested in studying weak topologies and weak star topologies, what are called as weak star topologies for these function spaces on which we are studying some dynamics. Which I'm sure you may have studied some of these things in your courses on function analysis.
Can you recall some references, Vivek?
So
maybe a few keywords so that he can look up further.
So certainly you should certainly learn about some function analysis. If you have not studied before, please do learn some function analysis, such as you can read some books such as on function analysis, such as let me see. There are good books on function analysis. For example, by Alberto Bresson has a book on function analysis, which is geared towards applications to partial differential equations. There is also another very nice book by Brazes, Chaim Brazes, which is also on function analysis and partial differential equations, which goes through the notions of weak topology and weak star topology in some detail. And now that you mentioned about dynamical systems, another very nice application or a very nice connection between partial differential equation and dynamical systems comes in the framework of the theory of homogenization, which is also what Professor Sivaji, Ganesh and I work on. So in this context, one studies periodic media. So we study medium. Partial differential equations are modeling certain mediums, and this media is maybe periodic in nature, or it may not be periodic, it may be non-periodic in nature. And in all of these cases, certain dynamical system notions come into the play very naturally. So for example, the notion of ergodicity is extremely important in the context of the theory of homogenization. So you can also read a little bit if you have done some preliminary study on partial differential equations as in this course and some preliminary study on function analysis. Perhaps you can read an introductory course on homogenization, such as by Siranescu and Donato.
I don't think Sandeepan is asking whether fractional differential equations further simplify into our non-PDEs or ODEs. See, remember this PDE or ODE is modeling certain physical process. And there are certain things which are modeled by fractional partial differential equations. It's not that you substitute a normal PDEs with fractional PDEs. It should arise naturally in the model. There are books written on fractional differential equations. You should look up for the applications part. Any questions regarding this course itself?
Sandeepan, do you have any more questions regarding the course or otherwise?
Yeah, maybe we wait for 5 minutes. If you have any questions, please ask. Sandeepan, are you taking the examination? So if you have any questions or comments, please, or doubts, please send an email to us. We will respond. You can find our email addresses online anytime. Math box, you have not asked any question? Yeah, we can talk on this later, Sandeepan. You email me, we will fix up some meeting and talk. Some students were inquiring during the live sessions by PMR of fellows that what will be the passing mark, etc. These are all very well defined on the NPTEL page. So I suggest students to refer to that. Okay, then we end the live session for today. Thank you, Vivek.
Thank you, sir.
Thank you, Professor Vivek from Kriya University. Thanks a lot.
Thank you.
Bye.